from Clicker. Now, do I have anyone from Israel here at all? No? Well, Ben is, and you're going to love him. All right? So a big round of applause to everyone for Mr. Ben Asaf.
Thank you. Thank you, thank you. Awesome. Well, hello, everybody. Super excited to be here. Hello. Yeah. So, as he amazingly introduced, my name is Ben Asaf. I'm originally from Israel. I am Click's CTO and co-founder. So, this will be our content for today. So, just a quick introduction about me, my background, about Clicka. We'll talk about cool recent developments with AI, right? We keep hearing stuff about it all the time. And next one, we'll talk about all the dark sides of those stuff. I mean, something's got to give, right? And lastly, we'll talk about how can we take big models and make them useful to us. Let's begin. So, in Clicka, what we do is we bring AI into real life. And what we mean by that is put it into actual use. More about productionizing those things. Less theoretical, more practical. And I want you to remember, bigger is not always better in this case. So, my name is Ben Asaf. I used to work at Mobileye, Intel subsidiary, as pretty much algorithms and machine learning operations. So everything that deals with the data, the models, how you experiment with them, running them on scale, on-premise, and finally delivering this into the hardware. As well, I worked at Hebrew University as a senior programmer in the parallel computation lab, which that essentially means is matrix multiplication. Everything in AI, machine learning, is matrix multiplication. You make that faster, everything is faster, everyone is happy, and most underrated job, by the way. So, cool recent developments. Machine learning. We keep hearing about it all the time. ChatGPT, Llama, new things. And I'd like to think about machine learning as a more simplified way. And that means, let's think about it as Lego pieces, right? I mean, you have a neural network. It's pretty much layer after layer. You put them together. Some layers work great with each other. Some layers don't work well with each other. And it's like Lego for adults, pretty much. So what we get is people keep stacking those up, and those models generalize better. They have more capacity to understand how to solve a problem and deliver you a good result. So with all this mindset, we get things like ChatGPT or Llama in open source. And all of these things are great. But it's actually so hard doing this. There are so many problems with AI, machine learning, the things that you don't get to read on the marketing side, the people who actually work on bringing those stuff into use. There is so much dirt. And I mean, if we keep comparing those to Lego, right? I mean, I look at this Lego piece. I'm not sure what is the purpose of this. And this can be a new layer in recent developments. You read about a paper that tells you, oh, this layer, it solves everything you wanted. And then maybe what they do is they put this into something like this. And I'm not sure how to use it. And what they do provide you is a marginal improvement over some arbitrary data set. So you get new LLM architectures, new neural network training techniques, new layers, new libraries, new data set, new hardware. A lot to process, and this keeps coming every week. There's no rest. So in order to reduce all this noise, just ask yourself 3 questions. Reducing all the marketing, hype, buzz, etc. Let's talk practical. Where are you going to run this? On what hardware are you going to run this? Are you planning to use public cloud, private cloud? maybe you're planning to run this on-premise, on your servers. Have you given a thought about how many GPUs you may need to run this model? Or maybe you're planning to run it on device. After all, we're an Android conference, right? So what would that be? What is the minimum device that you can actually run your model on? And again, what is the range of the devices you want to support? Only the latest one, et cetera. So, and latency problem. How fast do you want your model to run on? How would that scale as well? If you're planning to run this on cloud, for example, how much would that cost you to bring it down to that specific latency that would not damage your user experience, right? People have no patience. They want things to happen quickly. Whether it's running on device, cloud, they don't care. They just want it to happen. And lastly, budget. So in order to achieve that latency with that hardware, how much is it going to cost you, really? So again, is making things bigger help you? Is that marginal improvement over some arbitrary data set really going to help you solve your problems? So again, those three things, hardware, speed, cost, all you need to remember. So up until last year, people were really obsessed with training cost. How much did it cost to train that model? But in reality, the biggest price that you would pay is on the inference, because that's the product you're trying to run. You're putting it on cloud, on device, and especially on cloud, right? Maybe your phone makes an API request to cloud and gets a response back. You're going to save 1 million devices. Maybe you're sending an image over and sending another image over back again. How much would that cost? So inference is at minimum 6 times. I mean, it varies by use case, but ChatGPT, for example, spends tens of millions of dollars per month just to make that available for us. But there is a way. Models compression. So we can take expensive hardware and running AI on it. So this leads us to this. How can we tame those? And some 3 things. Can we reduce the size of the AI, or making it minimum 4 times faster? And what about more affordable devices? It is possible. Let's play a game. What you're going to see is 2 videos. One of them is the original model, before compression. And the other video is the model after compression. It's exactly the same model, just smaller. Let's see if you can pick up who is the compressed one or who is the original one. I'll give it like a few seconds. Oh, anyone has a guess? Yeah. Who thinks it's the left one is the original? OK. Who thinks the left one is the compressed one? OK. Pretty much the same, honestly. So this is how it looks like in reality. Now, this is an uncapped video. So what you're getting is the results from what you saw before, where we capped those so we can have an unbiased opinion about those. And now it's uncapped. So you can just see how the frame per second actually is. So of course, this applies to computer vision, as we can see. And the same thing can be applied to big LLMs models. So in order to achieve these type of things, you'll hear about probably these 3 popular techniques to make that size reduction a reality. One is called quantization, and basically is reducing the size of the parameters. Another one is pruning, basically removing, cutting, like as you would in a garden. And another thing is knowledge distillation, where you would most likely have a teacher model and a student model. And the student is smaller, but he gets his knowledge from the teacher. Very intuitive stuff overall. So the idea is you have something big on the left, you make it small on the right. So in reality, all these parameters that you keep hearing about, ChatGPT is minimum 175 billion parameters, 1 trillion parameters, basically just a number, okay? There's, like we said, it's consisted of layers. Some layers have parameters, and people tend to stack them up because the model learns this way. So the idea is, in order to represent one parameter, you would use 32 bits, 32 1-zeros. That's the information it holds. But the idea in quantization is to take it from 32 bits to 8 bits. Now, I wish it was as easy as right-clicking and doing add to archive, and you're done with it. But that mapping is actually annoying to get right. And a more intuitive example of how it may look visually. So here's the beautiful Namsan Tower in Seoul. This image is represented by 32 colors, analog to 32 bits. But how would it look like if we represented this image with 8 colors only? Can you tell the difference? If you look, maybe in the sky, you can see like that spot gets a bit dimmer. But does it really make a difference? We get the point, right? What about if we used 2 bits? We still get the idea. And the same thing applies to machine learning. We don't need all that capacity to focus on one thing. If my purpose was to understand there was a tower, I'm sure we could have even gone with 1 bit. So, and all these type of techniques basically allows us to have things on mobile phones or microcontrollers or maybe our laptops, et cetera, et cetera. And this how it pretty much looks. You can also come to our booth and we'll be happy to show you. So everything, of course, runs on device. And what we're trying to do is helping everyone who just wants to develop an app, putting an AI model into his whatever device so he can just focus on the important stuff. The same thing with super resolution. So let's say you have an old phone. You want it, like you have a picture that is very old, or maybe you just want to upscale an image. So it's very hard to tell. You can come to our booth. We'll be happy to show you the differences. Yeah, he's there, our employee. So basically, the same neural network, just smaller. So this enables us to do exactly this. Not having to use expensive hardware to do the same job. Essentially, same price, same hardware, 4 to 16 times more clients. Oh, in terms of like results, so right, quantization, I said it's very hard to get right or annoying to get right. And this is some of our numbers that we have. So you can see a table, sure, divided into tasks like classification, object detection, super resolution, and some popular neural network architectures, or let's say assembled Lego pieces that someone else put already for us. Our results pretty much achieve world's best in quantization, compared to solution A, solution B, where it even fails. So the idea is to reduce the size, but not at any price, but at one that keeps the model still intact and does the same job, just faster. And the same thing can apply to vision transformers, which we can say is a sibling of LLMs, because same principles are applied in vision transformers as they are in transformer LLMs. And you can see we get a 6 times acceleration or 9 times acceleration with a minimal accuracy reduction. So how would you like to develop an Android app that you can just put LLM on it? What about having some kind of drive-through that you can have a conversation with? Why not have a conversation with your car? I mean, why not go to the hospital and have someone help you where people may be very busy or understaffed? How about education? How about we put something to help guide people towards the right way when the teacher is busy? There's so many applications, so I just want you to have this in mind, how it may look like. and all without sending it to a company. Everything you do stays on your device. No privacy problems, nothing. So that was my speech. I have so much more to say, and I'd be happy to talk with you. And if you have any questions, you are more than welcome to come to our booth, which is by the C Lab.